Hi, everyone. My name is Ted Ding, and I'm a PhD student from Edinburgh Center for Robotics. I'm going to present our work, Variational Simultaneous Stereo Matching and Defogging in Low Visibility. As the title suggests, given a pair of foggy images, we seek to estimate a dense disparity map as well as a defogged intensity image simultaneously, both in the left frame. In this work, we focus on the situation of low visibility, which is not greater than 40 meters. Next, I'm going to justify our motivations. First is the outcome of the system. A dense disparity or depth map is essential for autonomous vehicles and can benefit high-level vision tasks, such as object detection and semantic segmentation. Meanwhile, a high-fidelity fog-free intensity image can help human driver plan and act safely. When it comes to sensor choice, this table shows the pros and cons of different types of sensors using a traffic light system. As you can see, LiDAR is very good at measuring depth and has very high angular resolution. However, it is very vulnerable to obscuring media, including fog. Imaging radar, as another active sensor, is also good at range measurement and is very resistant to fog. However, it has poor angular resolution, and most importantly, it lacks information on object appearance. Stereo camera can infer scene depth from disparity given that the correspondences problem can be solved. It has high angular resolution and has very rich information on object appearance. It is not very resistant to fog. However, even foggy image can still convey very useful information, especially for objects in the close range. Last but not least, a stereo camera is the least expensive sensor here. As for our strategy, we observe that the tasks, namely stereo matching and defogging, they are deeply linked via the scene depth. On the left-hand side, the pinhole camera model tells us that the scene depth is inversely proportional to disparity. On the right-hand side, how foggy an object appears to be actually indicates how far away it is from you. Such phenomenon is known as depth from scattering. Almost all existing stereo matching algorithms were developed under the assumption of clear scenes. Meanwhile, almost all literature on defogging deals with single images only. There's actually very limited amount of work on simultaneous stereo matching and defogging. Some early approaches, they were based on discrete optimization, which is difficult to parallelize for acceleration. More recently, deep neural networks have been used. However, the data acquisition for this application in real outdoor scenes is time-consuming at best, and not always possible. In contrast, our approach is based on variational continuous optimization, which is easy to make parallel for acceleration and does not require large-scale training data. This diagram gives an overview of our system. In a nutshell, it consists of two stages. The first one is the foggy stereo matching stage, which estimates a dense disparity map U from a pair of foggy images, IL and IR. The depth information embedded in U is then used by the defogging module to generate a fog-free image J. In the foggy stereo matching module, we devise an isotropic weighting scheme to allow for non-uniform penalty parameters at different pixel locations. We also include a customized regularization term, which encodes disparity cues from scattering via gradient alignment. Both of them are seamlessly incorporated in our optimization process. In the defogging module, we leverage a photo consistency check to enable the recovered depth information to assist defogging. This slide shows an animation of our method. The top two are the two input images. The bottom left shows how the estimated disparity map evolves as the optimization iteration goes. The bottom right shows the final defogged image. We evaluate on both synthetic and real data. These are the defogging results on the synthetic virtual KT2 dataset. Our method outperforms others in the SSIM metric and is the best at revealing faraway vehicles. As for the results for stereo matching, our method, again, performs the best both qualitatively and quantitatively by resolving small and distant objects. In addition, we investigate how the disparity results vary if the input images get flipped upside down. The motivation is to determine to what extent stereo reconstruction is based on context information, and to what extent dependent more generally on object geometry and reflectance. The results show that the optimization-based methods, including ours, are able to produce very consistent results, which is evidenced by the D10 metric change at the bottom right corner of each image. Whereas other methods witness noticeable performance degradation. These are the results on the pixel accurate depth dataset, which is a real dataset recorded in a weather chamber at a range of visibilities. Our method is better at removing fog from distant objects and preserving fine details. Our defogged images are therefore visually more appealing despite ranking the second best in the SSIM metric. Observing stereo matching results, our method has the lowest D10 metric error and is able to preserve fine structures to a greater extent. In addition, we plot the depth root mean square error against the visibility. The result shows that our method clearly excels at extremely low visibilities. We also conduct an ablation study by disabling modules in our system in turn and observing the impact on our system's performance. The key observation is that the anisotropic weighting scheme and the customized regularization term in our defogging module, in our foggy stereo matching module, greatly improves stereo matching results. The second key observation is that the transmission refinement module is able to suppress artifacts in the defogged image in the defogging module. To conclude, we proposed a variational pipeline of simultaneous stereo matching and defogging, which features a non-uniform weighting scheme allowing for different penalties per pixel, as well as an effective way of injecting depth cues from scattering via gradient alignment. For future work, we consider extending the current method to deal with multiple frames taken by a moving vehicle and adopting a more sophisticated fog model. For more information, please refer to our paper and supplementary material. We make our code publicly available on GitHub. Thank you very much for your time.